with relations.
Of course, they don't say anything about this bijection.
They don't say the bijection.
They say it's clear.
But they say there is a bijection.
No.
They don't even say the bijection. That makes me worry.
They don't prove
What
anything.
do they say? Exactly. Oh, but this is the paper by Zelevisky.
Yes.
Not the book, the paper.
Is there a book?
No, the book, no. The book is one
The other book, okay.
They say...
No, papers are like this.
The torsion freeness of this group is guaranteed by the following proposition whose straightforward proof is omitted.
Okay, which proposition?
The proposition is that the universal coefficient group is a free Abelian group, and it says it is generated by...
So it will tell.
Actually, they don't say about this family. They say you can choose the generators in a certain way, and this is one way to choose the generators.
But they say that way, no.
Yes, I mean, they say for any edge you can choose one of the two here. So and I choose this one.
No, it's difficult, yes.
The one which is closer, but you can choose the other one you also obtain.
Ma tu te lo sei preso perché tu sei brava, tu sei diligente.
Anyway, the proof is omitted. They don't say anything about
Io
it.
sono quello che non fa i compiti, I don't do the homework.
So that has been my interpretation of the proof. I want to tell you something different. So it's clear that we have an infinitely many degree of freedom in this coefficient group, despite the case of the exponents where everything was determined by an n by n matrix.
Dove l'hanno pubblicato? Non lo dice nemmeno. Where was
Questo è il chance. Now, we consider the coefficient group to have an additional structure of a semifield. Semifield. You know what the semifield is?
Guarda, ormai mi immagino tutto.
So this means that P is an auxiliary addition.
So there is already an addition that we write as a product, but there is another addition.
Now there was a product which makes P an abelian group, and then we also have an additional addition with respect to which P is not a group, it's a semi-group. Okay, so you can perform the sums of elements of P, but you cannot subtract. And then you have distributive law and associative law. This is also commutative. And that's it.
So it's like this. For example, the R plus is this.
R plus and right.
Just to understand.
I'm sorry, I was thinking of something else. Can you repeat, please?
No, non va bene dire così. Bisogna stare.
So my field, you have these two operations, sum and the product. It is a group. Both operations are commutative. It is a group with respect to the product, and a semi-group with respect to the plus. And then you have also the distributive law. So you can perform all the operations that we usually do, except that we cannot subtract. An example, of course, is the positive real numbers. It's an example of a semi-field. By the way, an observation is that a semi-field is automatically torsion-free.
With respect to
The product. Is automatically torsion-free.
Un po' confuso.
I can tell you why. This is
No.
So what is semi-group? It is that you don't have inverse, like
yes.
And you?
So what is the difference between semi-group and ring?
a semi-field and a ring.
No,
The distributive law is
il più non ha l'inverso, cioè come prendere z
it's
più.
different. I mean, the distributive law is the only difference.
Okay.
Distributive?
The difference between a semi-field and a ring and a commutative
Because
ring
distributive
Ah.
law
is the
is not,
distributive law.
distributive law is not symmetric.
No, of course.
No, ma no, non è vero, cioè, no, il per non c'è mica l'inverso in un anello, cioè, there is a-
No, se scambi l'operazione.
Ah, se scambi! No, scusa, però non è messa così.
Se consideriamo questo come più e questo come per, questo è un anello. No, perché la legge distributiva è scambiata.
Sì, sì, è vero, no? Certo.
Okay.
Cosa scambi? Cosa mi confondi?
Okay.
Ma scusa, so the torsion, wait for me because I have to understand. Torsion freeness is a property of multiplication.
Yes. And if you have a semi-field structure, then it is automatically torsion free.
No.
The multiplication.
You have to help me with this because there are many definitions. So
Oh, the definition is that p to the m equals 1 implies m equals 1 or p equals 1.
right. So if it is a field, you have this, right?
Yes, but also a semi-field. The proof is one line. I mean, I can.
No, because I wonder because on a field it's automatic, so you have the same here, right?
Yes.
It's a property of multiplication in mass.
If we multiply p times 1 plus p, so assume p to the m equals 1. Now we multiply p by 1 plus p plus e to m minus 1. We apply the distributive law and we obtain p plus p m minus 1 and then p to the n, which is 1. So this element with a bracket it is the same as this, and so p is 1. Okay, yes.
Wait.
This might be also the simpler proof to show that a field.
The field is
Oh,
also
field.
free, right?
No, no,
In fact,
finite, you have finite fields. How can, I mean, there has to be some condition. Torsion free with respect to multiplication, you're saying.
right. That's what confused me. Exactly.
Yes,
So you have to be sure
I need
that
the characteristic to be 0.
Yes.
Yes,
Right,
of
this,
course, of course, because I want this.
you have to be sure that that element is non-zero.
Yes. Okay. How can I be sure this is not 0?
Torsion freeness is I thought when you said torsion free you meant as a module, which means it has no zero divisors. But I have difficulty.
No, it's a simpler thing.
Simpler.
No, 0 divisor. No.
No, it is not that. Because
No, I
torsion
want this. This is the proof that they give. And so
They give-
that's not my proof. Eh?
Oh, wow.
Where is it? What do they say? I don't know. It's,
They give this proof.
um,
It's lucky how they use.
where is it they give? I think maybe they are characteristics here.
Page 513.
Can you tell the number of the proposition?
No, there is assumption P is automatically torsion free. Indeed, if P to the M equals 1, I just
Where
copy
is-
this.
Which example are you reading? Which numeration is different? Can you?
No, but maybe maybe it's not. the
Ah, but
same.
we don't have the 0. We don't have the 0 in semifield.
Maybe it's not the same.
We don't have a 0 because I want P to be a group with respect
Yes.
to the multiplication. So we cannot have a 0, I guess.
So what?
Dici che non c'è lo zero.
We don't have 0 in the semifield because we want P to be a group with respect to the multiplication. And I guess if we want a group with a distributive law, 0.
Well, zero is not,
cannot be an
zero is not
element.
invertible, but
No, it
it's,
says P is automatically torsion free as a multiplicative group because in fact,
Yes,
Okay.
yes, that's what we said.
okay, no, because torsion free is
Okay.
So what is the?
We are using the fact that there is no 0 in this semifield. Thanks.
So? I don't, yeah, then I don't.
This element cannot be 0 because, we
Because
don't
there
have the
is
0.
no zero. Why there is no zero?
Because P is a group with respect to
Right.
multiplication.
All of it. It's not like the field when you throw away the
It's
zero.
not. I guess.
The field you
yes.
throw away the zero. I mean, in definition of field.
Yes, you're right.
It's a matter of definition. But yes, they don't throw away the zero, okay?
I think there is no
Beh,
0.
in your example, you have no zero.
Yes, actually there is no 0 here.
Vabbè, quello è l'esempio però, questo è male, no?
No, se abbiamo bisogno di un elemento numerico per la funzione.
Sì, vabbè, però il fatto che dai l'esempio così non vuol mica dire che non ci può
No,
essere,
no, no.
cioè...
Yeah, we can consider R with 0 and then it is a semifield, meaning that the group, the set minus
this
0
is-
is a group.
this is very subtle because yeah, the finite field minus 0 is not a semi-field because you can keep adding, you can get to 0.
How-
Yes.
Finite field, so
Yeah, it's very,
this is subtler than it looks.
yes. Well, we will see the main example is the tropical semifield. I will show you this example in the near future. Hope today.
Tropical like in tropical geometry?
Yes,
No?
it's exactly that.
Eh?
Yeah. So I give you this definition. If P is a semifield, we say that an exchange pattern
You haven't told us yet what's this plus. What is plus? For P?
is an auxiliary addition satisfying the axiom. For the moment, I don't. It's a general semifield. But then we will consider the plus to be the minimum of two integer. I will show
No, you have to, I mean, you have to
I can give
define
you the
it
example
yet.
before going on.
I mean, you have to define it though. I mean, P you have. P is something you have in your hand, right?
No. We consider
No,
P with a plus sign. With a
No,
plus.
I understand. For now, P is any set, whatever, but
Yes.
very soon it will be our P.
Yes, but we
Not
cannot
now.
impose this additional structure on any group P.
No, I understand, but you're not telling us what it is in our case yet.
Yeah, I can tell you this example of semifield, which will be our main example.
Yes, that's.
Yes. Suppose P. Yes, P. Actually, we can impose it. We can, because we take P to be the free abelian group. Huh?
P is the one that we know.
Yes, free abelian group. Generated by elements called Pi. This is finite, eh? Free abelian group generated by finite set.
Which is not our case. What of you say?
It's not our case because we don't have a finite generation, but maybe the definition goes works also if the generating set is not finite, I guess.
Okay.
Yes. Yes. So the typical element, yeah, we may think I to be. Well, let's consider I to be finite. The product I in I, EI, the AI is a typical element in this group, where AI are integers. EI. EI. This is by definition the product of PI to the minimum between AI and PI. Okay.
Oh yeah, this will go even if it's not finite because
Yes, yes,
any
yes.
expression will be a
Finite.
finite is
Yes. All the others are 0, and so this definition can be performed also if the generating set is not finite. Okay. Of course, we have to verify some the axioms of the semi theory, but I don't want to do it now. Okay. Well, in particular, if these exponents are non-negative, this is in some sense the greatest common divisor of these two elements. If you consider it as a polynomial, as a monomial. In any case, you consider the minimum of the exponents of the two elements. So the result here is that oh no, I have to give you a definition. The definition I was writing at the video. So that an exchange pattern is normalized if for any edge P prime I, then the sum of the coefficients PIT plus PI T prime is 1. Okay.
yeah, it makes sense because we'll get rid of all the common divisors, right?
Yes. Yes. So, and if we restrict our attention to normalize exchange pattern, we have a situation which is very similar to that of the exponents that we saw last time.
Exponents? Which exponents?
The exponents of the monomials MIT.
Yeah, I don't understand your comment.
My comment is the next proposition.
Okay.
Remember, the exponents were all determined by the exponents of the monomials around T0.
Right.
And if we restrict the attention to normalize exchange pattern, the same happens for the coefficients.
Ah,
We can fix the coefficients around T0 and then all the others are
no, it makes sense.
determined.
Yes.
So this is the exact proposition.
Yes, because the axiom 4 is the one that kills the greatest common divisor, right? That's the problem, because you divide somehow. So you lose track of it. But if you normalize, axiom 4 will allow you to get all the things. Isn't that right, what I'm saying? It's axiom
Yes.
4 that
Yes.
is the role, right?
Yes, I mean the problem, if you remember from the very first lecture on cluster algebras, we realized that what is determined was the quotient of these
Right.
coefficients. But of course, if you know the quotient
Right.
and the sum, then the two elements will be determined. So that's
That's it.
what I'm going
So
to
it's
show.
funny because there are some very simple ideas that get overly complicated with all this machinery. I wonder if they're doing something that is really new with this, because otherwise there's no reason to complicate. Why? I don't understand.
Be patient, be patient.
I know it's one of my worst sides.
So, proposition, given 2n elements Qj and Rj in P such that Qj plus Rj equals 1, and of course in the family of matrices BT satisfying the axiom for an exchange pattern. BT satisfying 1 and 2 above. Then there exists a unique exchange pattern such that the fixed vertex T0, T0 is fixed, which is T prime. Every time we have this, we want P I T0 to be Ti and P I of T prime to be Ri. Okay. So if we fix all the coefficients of the monomials around T0, then all the rest is determined. Want to make a break?
No, now it's because at 11 we have another class, so it's really.
You have a class at 11?
Yes, you know that
Yes,
Stephen, well, 11 something is not
you're right,
really.
you're right. So maybe, I think.
But don't rush, because
No.
if you rush, I don't understand.
Be proof. We call uj of t the quotient pjt divided by pj t prime, where t and t prime are like this. First of all, we want to show that Pj and Pjt prime can be expressed in terms of Ujt. If we know that their sum is 1.
No, sorry, I want to ask a question before this, right? Okay, so there is the exchange pattern tells me about the whole cluster, right? And not just one step.
Yes.
But here, so this, I don't know, because you say T0 is fixed, right? That's what you said.
Yes.
So I don't understand very well because like You see what happens at T0, you know what happens at T1, which is distance 1 from T0. And how about the rest? I'm confused.
The rest is automatically fixed. That's what I want to show. We already know that the exponents of the monomials are determined by the last lecture. And I want to show that also the coefficients are uniquely determined if we know that
Okay.
There's something.
Okay,
the
no.
unique, of course, this is a unique normalized exponential.
Normalized such that this happens for all I and for all T primes. That,
Well, this,
or for one, I don't understand the quantifiers here.
well, this is for all I, for all
For all
vertices,
possible.
yes. So we have these two n elements.
Yeah, that was confusing me. So it's not for T prime, for all T prime.
For all T prime around T0.
Corresponding to the all I's. Okay, thank you. Because I was like, one is not
Yes.
enough. Okay.
Yeah, yes, this
For all I
for all.
and T prime corresponding. Okay. Sorry.
No, no,
It's
you're right. Was
getting
not
confused.
precise. So if we assume that
No, but the I turned to a J there.
hmm?
The I turned into a J in the next. No.
Right, you also enumerated the
Eh?
those guys using J's.
No, I mean, I get confused, but you help. No, it's all J's, right? I'm just... No, ma guarda, su quelle piccole cose che già uno fa fatica, io poi sono anche incoglionita, cioè... Se uno è sveglio non è un problema. Ok.
Okay. So if we know that the sum of these two elements is 1, then let's see, Pj T prime, we can write it as Pj T prime divided by Pjt plus Pj prime. And then if I move this below, I have 1 divided by Ujt plus 1. Okay. If we move this below here, then I have yes, this divided by this is Ujt, and this divided by this is 1. So Pjt prime has this expression, and therefore Pjt, which is Pjt prime times Ujt, yes, this is Ujt divided by Ujt plus 1. Okay, so we can express both Pjt prime and Pjt in terms of their quotient. And now, what they do is to translate the condition that we wrote in the very first result of today for the relation among the P as a relation among the U. So we have this. Okay. This is T prime with J
mi sono confusa un'altra volta. No. So this T is not the T0 you're fixing.
No, this is two any vertices.
So now we're taking two any vertices with this.
Two adjacent vertices.
Okay.
If
Okay.
So these are these two elements, and then take any I different from J. We have the T1 and T4. So T becomes the T2 and T prime becomes the T3 in the first term. Let's see. So let me write back the relation among the PIs. We have PI T1 times PI T2 times P J T8 to the max J I T3 0 equals P I T4 P J T2 max B J I T3 0. So let me see. We divide this by PIT4 relation. By PIT1. So this quotient is U I of T prime. Ui of T prime is pi, T prime is T3, okay? This pi T3 divided by pi T4, where T4 is the other vertex of the edge labeled by I. Okay? I leave this maybe. This is equal to, I will move this on the other side. This quotient PIT2 divided by PIT1 is UI of T. Okay. And then we have P J T2 maximum of P J I T2 0 divided by P J T3 maximum of P J I. So T2 was T and this is T prime. Then PJT2, because this is PJT and this is PJT prime. So that you only have T and T prime. So PJT is this. So UI T times U J T divided by U J T plus 1 0. And then this BJT prime was this. So I can write UJT plus 1 to this exponent. Maximum
That is clever.
BJI t prime is minus BJI of t because of the notation. So I write minus BJI of t 0. So what do we have at last?
We have what we want.
Yes, more or less. UIT times.
Well, you're finished, right? Why are you writing this?
Yeah, I want to simplify it a little bit. I want to
But it's not necessary.
Yes, but I want a simple expression. Yes. No, it's not necessary. You're
But
right.
for the proof
But
is finished.
for the proof
because,
is finished, but I want
T
a
prime.
yes, because we have expressed the UI t prime in terms of UI and UJ of t. So that's the end of the proof. But I want a formula which is as simple as possible because I will need it later. So this remains the same. UJ t to the max b j t 0. Then we have this element which is equal to this. So we have to observe that this is always yes, UJT plus 1 to the minus BJI of t. Let's see why. So if BJ of t is positive, then this disappears and get this to the minus BJI of t. Okay. If BJ of t is negative, then this disappears, and yes, we have this element 2 minus BJ of t. We just simple observation to have this form. Okay, maybe we can stop here.
No, yeah, because then he has to speak at 11. I mean,
Oh, okay,
it's a
okay,
class.
that's fine.